So now that we've talked about these dimensionless parameters and figured out how to calculate them, the question is, what can we do with them? And so it's actually pretty interesting, because what happens when we're looking at these dimensionless performance characteristics? If you have two items that are geometrically similar, then the coefficients, no matter what, have to match up. So if I look at a pump and say, okay, so if I look at a pump and go, okay, well, I have a capacity of coefficient of one pump, well, that's going to have to equal the capacity of coefficient of the second pump. That's geometrically similar. Has to be geometrically similar. Okay, great. So they match up. What does that mean? Well, it means that Q of 1 divided by N1 D1 cubed has to equal all that stuff at the second pump. And so now this is where you get into, well, let's say you know the coefficient, the capacity coefficient, or more likely, what you know is I know what the impeller speed, the diameter, and the flow rate of one pump is. So what happens if I have a pump that's got a different impeller speed and a different impeller? Well, then you can find that last piece of information. You can find that flow rate. And so a lot of this comes down to, this is where I was talking about pumps being similar to themselves. Well, let's say that pump 1 and pump 2 are the exact same pump. It's just you've got this one here, 0.1, this one's running at 1500 RPM, and you're like, okay, what happens when I run it at 1000 RPM? Well, you can change that number to 1000. That doesn't change. The only thing that's going to change is Q. And so you're going to be able to back work out what Q is. If you look at the coefficient of power, so if I have two similar pumps and the coefficients of power have to be the same, what is that going to do for me? And once again, if we're looking at all these pumps that are just moving water, and you look at it, it's like, well, there's the brake horsepower, rho, n cubed d to the fifth of the first pump is going to equal all this of the second pump. So if you're using the same pump, so it's similar to itself, and you're just trying to figure out what the change is if you change the fluid, well, you can change that density between the two of them and be able to calculate out how much is, the brake horsepower going to have to change if you keep the impeller speed the same. Or it could be, what do we have to change the impeller speed to make the brake horsepower work out to be the same? And then you can flow that back into your other ones. Once you figure out that information, you can flow that impeller speed back into your coefficient of head and coefficient of capacity equations to figure out how the head and the flow rate has been impacted by those changes. And so a lot of times what will happen is, okay, we have one pump. We want to make another style. We want to take that pump and we want to make a couple of different versions of it. How is it going to act? Do we have to build that pump and test it before we can do it? No, you can actually take a look at this and go, okay, well, I know this pump is here, and this other one's geometrically similar, so I can calculate out what all of the data for that geometrically similar pump is going to be. And then we can use this just like they use the experimental data from a plane in a wind tunnel to predict what the small plane's going to do, or what the big plane's going to do based off the smaller one. And that's what we'll actually do in the next problem.